So next we're going to talk about another solid of revolution and finding volume using the washer method. So when you revolve a region bounded by two different functions around an axis of revolution, the resulting solid has a hollow space. So you can kind of see the hollow space right here. So let's take a look at this demonstration. So here we have a function y equals f of x, and here we have a function y equals g of x. And we're going to look at the region from A to B. And so this would be the shaded region, which we could find. And what we want to do now is rotate this around the x-axis. So you can see the area of this region then would get rotated all the way around the axis, like so. Okay. And if we draw the solid as we go, you can see the solid of revolution that's being created here. And you can see that because our two functions aren't on the axis of revolution, we do get a hole right there in our solid. And if we make this transparent, then you can see it a little bit better as well. So basically what we need to be able to do is find all the volume of just the solid portion. So it's going to basically be the volume found by revolving f of x around and then subtracting the volume of revolving g of x around. Okay, so before, when we revolved it around, our cross sections were actually circles with a radius of r, and our area here was just pi r squared. But if we were to take this section right here and revolve it around the x-axis, we no longer have disks, but instead we would get washers. So here would be the circle formed by f of x, and then here would be the circle formed by g of x. And what we want to try to do is find just this area right in here. So you can see now that we actually have two different radii. So I'm going to call this r sub 2 and r sub 1. And if we want to find just that highlighted area, we would do pi times r sub 2 squared minus pi times r sub 1 squared. And it turns out that we can factor out our pi. We would have pi times r sub 2 squared minus r sub 1 squared. Now, the only difference here that we have to think about in a solid of revolution is that we're going to have these cross sections taken all the way along. And so again, we're going to have this idea of a delta x or a dx that we're multiplying to find the actual volume. Okay? And if we apply this over here to our actual solid, you can see then this little length right here, and hopefully you can see how that disk would apply right there. Okay, so first let's deal with a horizontal axis of revolution. We're going to go ahead and just make a region here bounded by two functions. So I'm just going to do this function on top and then this function on the bottom, and we're going to revolve this around this horizontal axis, and it's going to go from A to B, and I'm just going to draw my y-axis in here. And so if we were to revolve this around, it would actually get mirrored on the other side here. And then, of course, we would get kind of the inside right there. And we would also have the outside right here. And it'd be three-dimensional, so we would see that around the back side there. Now the biggest thing to think about here is we need to find our representative rectangle. Okay, so we'll just draw it right there. And you can see the width of this rectangle is going to be delta x. And so what we need to do is actually determine the height at the top and then at the bottom. So the top we're going to call capital R of x, and the bottom we're going to call lowercase r of x. So if we want to find this volume now, the volume is going to be pi, okay, because we're dealing with pi r squared, and then the integral from a to b of capital R of x squared, and that's the top one, minus lowercase r of x squared, and that's the bottom one, times dx. Okay, so very similar to what we were doing with the disk method, but the washer method has to take into account this volume that's not going to be there, and we do that basically by subtracting out this hollow portion on the inside. Alright, let's take a look at a vertical axis of revolution now. So now I can just draw my functions. Maybe it would look like this, and maybe like this. And we want to revolve this around a vertical axis now. And so this would just get mirrored on the other side. Okay, and then this whole thing would get spun around. So here would be the outside of our solid, and then here would be the inside of our solid. And I'm just going to draw the x-axis here. And so when we look at this, our limits of integration are going to be from c to d. And right here would be our c, which is a y value. And then right here, okay, corresponds to here, would be d, which is also a y value. Now, we also want to draw our representative rectangle. And you can see now the width of the rectangle is going to be delta y. And what we need to do is find these values right here, which are actually going to be x values. So on the outside, we're going to have capital R of y. And then on the inside, we're going to have lowercase r of y. We need to find these functions in terms of y. So we're basically going to be solving for our x's. And so now, when we look at our integral, the volume is going to be pi times the definite integral from c to d of capital R of y squared minus lowercase r of y squared, and then with respect to y. So again, you can think we just need to find the outside, the entire solid, and then subtract that little hole or the inside solid to find our overall volume. Alright, so let's try some examples here. So it says find the volume of the solid form by revolving the region bounded by the two graphs about the given axis of revolution. So here we have y equals square root of x, and on the bottom we have y equals x squared, and we're going to revolve this around the x-axis right here. Okay, so I like to draw that there. And this is going to look something like this. It's going to be reflected. And we'll have a nice open circle right here. And then the outside right there. And then of course we're also going to have our inside circles there. Let's draw our representative rectangle so we can see what's happening here. You can see that the width of the rectangle is delta x, and we need to identify, well, this height is going to be square root of x, and then this height on the bottom is going to be x squared. So this one is going to be our capital R of x. And this is going to be our lowercase r of x. Okay, so I think we have everything we need except for our limits of integration. Well, it's going to go from 0 here all the way to 1, and you can see that's where the two intersect. So our volume is going to be pi times the definite integral from 0 to 1 of capital R sub x squared, so square root of x squared, minus lowercase r of x, which is x squared, squared, and this is going to be dx. Okay, we could just put that into our calculator, or we can clean it up just a little bit here. So it'll be from 0 to 1. The square root of x squared is just going to be x, and then x squared squared will be x to the 4th, and this is going to be dx. And when we solve this in our calculator, we get an approximation of about 0.942 cubic units. All right, let's try example B. So in example B, we're looking at the region bounded by y equals x squared plus 1, which is right here. The line y equals 1, which is right here. And let's go ahead and change this to x equals 2. Give us a little more room to work. So x equals 2 is going to be right here. So you can see the region we're talking about is right in here. And we're revolving this around the y-axis. So we're going around the y-axis right here. So this would create a mirror image on the other side of our graph. And then this would become a three-dimensional kind of image here. And then we would have kind of an open, hollow center here, just like that. Okay, so looking at this, our representative rectangle now would be horizontal. And what that tells me is that the width of the rectangle is delta y, and I'm going to need to find capital R of y and then lowercase r of y. So instead of having y equals x squared plus 1, let's see, I would subtract 1 and then take the square root. I'm actually going to get x equals the square root of y minus 1. And that's going to be our inside curve. So that's actually going to be our lowercase. Now in the case of uppercase, this is the line x equals 2. So this is just x equals 2. Okay, so to find our interval now, it's going to be from here all the way up to where they intersect. So we do need to find where they intersect, and that's going to be where these two equations are equal to each other. So where does the square root of y minus 1 equal to? Well, we'll square both sides, and then add 1, so y would equal 5. So it is at the point 2 comma 5. Visually it looks like that. So our limits of integration are going to go from 1 up to 5. Our volume is going to be pi times the integral from 1 to 5 of our outside function, or the capital R, which is going to be 2 squared, minus the inside function, or the lowercase r sub y, which is the square root of y minus 1 squared, with respect to y. And we can clean this up a little bit. So it's the integral from 1 to 5. This is going to be 4 minus y minus 1. Okay, and if we change the signs here, we would actually get 5 minus y dy. And if we solve this using our calculator, we're going to come out with approximately 25.133 cubic units. Alright, in our next example it says find the volume of the solid formed by revolving the region bounded by the two graphs about the given axis of revolution. So now we have the line y equals x squared, okay, which is going to go to 1, 1, 2, 4. Okay, and the line y equals 0, which is right here, and then x equals 2, okay, which is right there. And now we're going to revolve this about the line y equals negative 2. So here is our axis of rotation here. So we just want to draw that we're revolving around there. So now, if this is going to mirror on the other side, notice that this is 2 away, so we actually have to start 2 below. And here would be the mirrored image. And we're revolving it, so we get this sort of three-dimensional, like sideways volcano-looking thing. Okay, and here's the region that we're actually revolving. And our representative rectangle in this case is going to be a vertical rectangle. Okay, so in this case we need to find our capital R of x and then our lowercase r of x, and then the width, of course, is delta x, and the limits of integration here are going to go from 0 all the way to 2. Okay, so this is where it can get a little bit tricky if your axis of symmetry here is not y or x axis. So when you're looking for that r of x, the radius of the disk. Okay, and so we basically have to find the length from here down to your axis. And that's really your r of x. When you're looking for lowercase r of x, the same thing here. It's the radius of the inside or of the hole, and that's going to be lowercase r of x right there. Okay, so here's where we just have to think. We need to find our capital R of x, or our big radius. So this distance here is 2, and then this distance here is x squared. So capital of R of x is going to be x squared plus 2. Lowercase r of x is just this distance right here, so that distance is just 2. So our volume is going to be pi times the definite integral from, well, 0 to 2 of our big radius, so that's going to be x squared plus 2 squared, minus the little radius, which is just 2 squared, with respect to x. When we approximate this using our calculator, we get 53.617. So the biggest thing here is learning how to identify your capital R of x, or your big radius, and the lowercase r of x, or your little radius. And it really is helpful if you draw the graph so that you can see physically what you're trying to find the length there. Alright, let's try our next one. I want you to give this one a try on your own. See if you can come up with your capital R of x and your lowercase r of x, and then find the volume of the region. Alright, welcome back. So go ahead and check your drawing. Verify your vertical rectangle. And then check your capital R of x, and that's just going to be 5 always. And then your lowercase r of x, well, it's going to be 5, but then subtract the function x squared. So we get 5 minus x squared. And then just apply it using the disk method, and you should get about 63.670 cubic units. Alright, let's move on. In letter C, we still have the same region that we're bounding here. We still have y equals x squared, y equals 0, and x equals 2. And now we're going about the line x equals 5. So now we have a vertical axis of revolution. Okay, so if we're going to draw this, we need to make this symmetrical on the other side. Okay, and then we'll just kind of make this a little bit more three-dimensional looking here. Here's the inside, and then here's the outside. And the area that we are revolving is right here. Okay, so let's draw our representative rectangle here. Okay, so you can see that this portion from here to here is going to be our inside radius, or the small radius. We'll call that lowercase. And then on the outside, from here over, that's going to be our capital R of y. Now, to find this, our small r, you can see very easily. You can see it goes from the line x equals 2 to the line x equals 5. And so this is just going to be 5 minus 2 is 3, and you can see that it is 3 wide there. And if we want to find uppercase or our big radius, to get this one, we actually take this entire length here from 0 to 5, which is 5, and then we subtract the length to get to our function. And in order to know what that is, we have to solve y equals x squared in terms of y. So we really have x equals the square root of y. So the distance from here to here is just going to be the square root of y. So if we want to find r of y, it's going to be 5 minus the square root of y. Okay, so again, capital R of y is 5 minus the square root of y. Lowercase r of y is just going to be 3. And so let's find our volume. It's going to be pi. We always think pi r squared. So our limits of integration now have to be in terms of y. So we're actually going all the way from here, from y equals 0, up to here, which is 4. Now how do we know it went up to 4? That's where this intersection happens. Okay, so that's where the square root of y equals 2. Okay, because if you plug in 4 right here, that equals 2. So limits of integration are 0 to 4 of capital R sub y, which is 5 minus square root of y squared, minus lowercase r of y, which is 3 squared, and with respect to y. And using our calculator, we get an approximation of 58.643 cubic units. I want you to go ahead and try letter D on your own. Go ahead and make your drawing, sketch everything out, find your representative rectangle, find your capital R of y and your lowercase r of y, and then apply your formula and find the volume. Go ahead and pause the video and come on back when you're done to check your work. Alright, welcome back. So go ahead and take a look at your drawing. You should have horizontal rectangles here. And if you want to find capital R of y, that distance is just going to be from here to here. And notice that this was 2, and this is also 2, so we got 4 there. And then if we're looking for lowercase r of y, again, the distance from here to here is 2, and then from the y-axis to our function is going to be the square root of y. So if we add those together, we get the square root of y plus 2. So again, capital R of y was 4, lowercase r of y was the square root of y plus 2. Okay, here is your definite integral, again from 0 to 4. And you should have gotten about 58.643 cubic units. Alright, so that is using the washer method to find volumes of revolution.